Hello, my name is Santiago Mol Lopez, and in this video on derivatives, we will revisit the concept of function composition and calculate the derivative of a composite function. The prerequisites include basic understanding of elementary function derivatives. However, I will also review these derivatives during the video. Let's begin by understanding what function composition is. Imagine we have two functions. The composition of f with g acting on x is defined as f applied to g of x. It's a somewhat unusual definition, but it becomes clear with the exercises we'll see next. And of course, this composition is called the composite function of f with g. A note: the domain of the composition of f with g is the set of all values of x from the domain of g, such that g of x belongs to the domain of f. It's important to remember that the domain is the set of values where a function is well defined. Let's see an example of how a composition of two functions is calculated. Suppose that we have that f of x is the sine of x and that g of x is x squared plus 1. How do we calculate f composed of g acting on x? It is very easy. We apply that strange definition we saw at the beginning and we put f acting on g of x. Next, what we do is change the expression of g of x by the corresponding function. In this case, g of x is x squared plus 1. Well, we write it. Following, we are going to calculate the value of f of x squared plus 1. Note that the function f of x is the sine of x. That means that each value that I put in this x is reflected here. For example, f of 2 would be the sine of 2, f of 3 would be the sine of 3, f of 4 would be the sine of 4, f of 1 squared would be the sine of 1 squared. The important thing is that now f of x squared plus 1 would be the sine of x squared plus 1. This here is a composition of f with g. It's a composed function. What happens if we calculate the composition backwards? For example, g composed with f. It's exactly the same. We apply the definition by having g act on f of x, which is precisely the opposite. Next, I'm going to substitute the function f of x with its example expression. I would have g of sine of x. Then we take the function g and replace the variable x with the sine function. In this case, it would be the sine of x squared plus 1. Important note, observe that the two options are not the same. Therefore, f composed with g is not equal to g composed with f. Now, the question that arises is how to differentiate functions of this type. Normally, we are all accustomed to functions like sine of x, cosine of x, in which there is only one x inside the sine. When things get a bit more complicated, it's not so easy to differentiate. I also remind you that the derivative of sine is cosine, and the derivative of cosine is negative sine. What is the sine of x squared plus 1? We'll try to clarify this with the property of the derivative of the composition of functions. Suppose that we have two functions that can be composed. We calculate the composition of f with g, and we want to differentiate it. According to this formula, the derivative of the composition is f prime acting on g of x times g prime of x, f prime acting on g of x without differentiation times g prime of x. How does this apply? Let's see an example. The same one. The function sine of x and g of x equal to x squared plus 1. As you remember, the composition was sine of x squared plus 1. How do we differentiate this composite function? We're going to see it. According to the property, f composed with g prime of x would be equal to f prime of g of x times g prime of x. Here's the copied text. Let's go step by step. What is f prime? If f is sine of x, f prime would be cosine of x. What happens is that it's evaluated not in x, but in the function g of x without differentiation. That means I would write something like this. The derivative of sine is cosine, and instead of putting x, I substitute it with the function g of x, which is x squared plus 1. Let's continue a little bit more. It's multiplied by the derivative of g prime of x. What is the derivative of g? If you know what g is, its derivative should be easy. Here, it is x squared plus 1. The derivative of x squared is 2x, and the derivative of 1 is a constant that adds up. It is 0. Therefore, the derivative of x squared plus 1 is 2x, which goes right behind, multiplying. Do you see the scheme? F prime is the derivative of the function f acting on the function g of x multiplied by the derivative of the function g of x. This helps me rewrite the derivatives of elementary functions while applying the chain rule. That means we'll be generating more general formulas, which will be much more useful when calculating certain derivatives. We will start with one to which the chain rule doesn't actually apply. This function is the derivative of the function x. Its derivative would be 1. Next, we are going to review the derivative of the function x raised to the power of n. I want to emphasize that this is one of the most important derivatives that you can use, and it is applied frequently. X raised to the power of n. its derivative is n by x raised to the power of n minus 1. How is it calculated? The exponent n comes down in front, and we subtract 1 from the existing exponent. It is the same as applied a while ago. The derivative of x squared is 2x. Let's continue by generalizing this property, this derivative. This one is very important. Notice that the only thing I've done is, instead of writing x, I've used g of x raised to the power of n. While it's not exactly the same, the procedure is very similar. By applying the formula we've seen for the derivative of a function composition, I obtain the following derivative. I lower the n down in front, subtract 1 from the existing exponent, and then I multiply by g of x without differentiating, followed by multiplication with the derivative of g of x. This is important, and I want to emphasize its significance. Here I explained a little bit that the n goes down, I subtract 1 from the exponent, and the g of x is placed as a derivative multiplied at the end. Let's continue with the sine of a certain function g of x. You should all remember that the derivative of the sine of x is the cosine of x. Now what happens when I have the sine of g of x? You've seen it in the previous example. Let's see how this would look. The derivative of sine is cosine. The function g of x remains without being differentiated. We then multiply this by the derivative of the function g. Next, let's see what happens with the cosine of g of x. Here I would also need you to remember one thing, that the derivative of the cosine is the minus sine. Look, the derivative of the cosine of a certain function g would result in minus the sine of that function, without further differentiation multiplied by the derivative of the function g. The same applies to the exponential function. When calculating the derivative of e raised to the power of g of x, it resembles the derivative of e raised to the power of x. Do you remember that derivative? It's e to the power of x. It is the same. What happens when x is replaced by a function g of x? It would be exactly the same function, multiplied by g prime of x. And what about the logarithm of a function g of x? What was the derivative of the natural logarithm of x? It is 1 divided by x. What happens when x is replaced by g of x? Observe, 1 divided by g of x multiplied by the derivative of g prime. Here, a quick note. I consistently include g prime at the end of these expressions. In many books and texts, you'll find that the derivative of the natural logarithm of the function g of x is written as g prime of x divided by g of x. However, I present it this way to highlight that, in the end, I'm always multiplying by g prime. Let's continue a little bit more. What occurs when e raised to the power of g of x is replaced with a raised to the power of g of x? It's based on the same derivative as when a is raised to the power of x. But look, it adapts. It would be a raised to g of x multiplied by the natural logarithm of a. This is always included in this derivative times g prime of x. Again, the derivative of the exponent here. What happens when I use the logarithm with base a of g of x? It would be 1 divided by g of x multiplied by the natural logarithm of a multiplied by g prime of x. They always end up the same with g prime of x. The first part of the expression is based on the structure of the derivative without the function g of x, simply the function of x. Let's explore 3 more functions that are particularly important for integration. They frequently appear in integrals and can provide efficient solutions to many problems. What is the derivative of f of x of the arctangent of g of x? Based on the structure of the derivative of the arctangent of x, which was 1 divided by 1 plus x squared, this one yields as follows. 1 divided by 1 plus g of x squared by g prime of x. We can deduce the same from the arcsine and arccosine functions. Here you have their expressions, which are also derived from the derivatives of arcsine and arccosine. I'll move ahead a bit now because I want to see the examples better than the list that you can consult at any time. Let's see an example. When we have a function raised to the power of n, its derivative, as reviewed in the previous list, is n multiplied by g of x raised to the power of n minus 1 times the derivative of g of x. Here, g represents the original function without differentiation, while g prime represents its derivative. How does it apply? Let's see a very easy example. How do you find the derivative of the 4th power of x squared plus 2x plus 1? I'll bring the 4 down in front, subtract 1 from the exponent, and then multiply by the derivative of what's inside. Observe the 4 goes down here, I subtract 1 from 4, leaving me with 3. Here I leave what's inside without differentiating, as you have it here. Now, I'll multiply by the derivative of what's inside the parentheses. The derivative of x squared is 2x, the derivative of 2x is 2, and the derivative of 1 is 0. So I have 2x plus 2. Another example, sine of x squared is the same. I have a function, and the n here is squared. So how do we differentiate this? The 2 comes down in front, the sign remains unchanged, we subtract 1 from the exponent, and then we multiply by the derivative of the sine, which is the cosine. Here's another example. The natural logarithm raised to the power of 1/2. How do we calculate it? The half is brought down in front, and when we subtract 1 from the exponent, we get minus 1/2. This is why you see it here. I keep the natural logarithm unchanged, and then calculate its derivative, which is 1 over x, and place it at the end. So far, we have seen how the rule of differentiation for a composition of functions is applied. We've organized a table of derivatives that includes a specific function g of x, allowing us to apply the chain rule effectively. I trust that all of this information has proven to be helpful for you. Thank you very much for your attention.